right, take out your memory. If your memory is not sufficient, take out your purple sheet. Right? So you don't have to take out your purple sheet if your purple sheet is completely memorized and you feel like you are an expert in all of these. All right. Glad to see everybody taking out their purple sheets. Advanced integration techniques often involve you have an integral that is close to one of your purple sheets, but not perfect. Which one is it closest to? No, I don't think tan inverse, because this one has a square root.
No.
Oh, sine inverse, it looks pretty nice, doesn't it? Sine inverse has a 1 minus x squared. Right? And this one has a 4 minus x squared. But it seems very close. So how could we manipulate this to get a 1 minus instead of a 4 minus? We could factor out a 4. So here's our idea. We start by factoring out the square root of 4. That's really tiny. I'm gonna do two things. I'm going to make it a little bit bigger, and then I'm going to erase it. And show the work a little bit slower. Can you see if you factored out a 4, you would have 4 minus 1 over 4. Sorry. If I factor out the 4, factoring out means you have brackets, right? I factor out that 4, I would have 1 minus, and then I would have x squared over 4. Are you okay with that factoring out of a 4? Now factoring out that 4, using your rules for square roots, I am going to write it bigger, but I'm going to put it in here afterwards. But I don't want to write it super small to begin with. Can you see that factoring out that 4, you would have 1 over the square root of 4 is 2. And then inside of my square root, I could have 1 minus, but instead of x squared over 4, I'm going to write x over 2 squared. Does that make sense? Yes. I'll just make that tiny and put it in there where you would put it in your notes. Actually, I'm not going to make it that tiny. I'm going to rearrange things here a little bit. Oh, no. So I just did an extra step. I factored out that 4. That would allow me to bring that out as a 2 in front. And then I would have 1 minus x squared over 4, but I changed the x squared over 4 to x over 2 squared, so it really looks like my purple sheet. We're either bringing out our memory or bringing out our purple sheet. Is your memory good, or do you just not have your purple sheet? I'm just checking, right? He might have been like feeling like I don't necessarily want to admit that I lost my purple most important sheet to this unit. So, okay. Now, I find with sine inverse, cos inverse, tan inverse, even though this is a nice format one, where it's just a simple chain rule, somehow with the inverse ones, simple chain rules are never just simple because of the So you might, even though it's a simple chain rule, want to use substitution. You might want to make u equal x over 2 or 1/2 x. Then your derivative is just 1/2 dx. And then things work out really nicely because this 2 out in front is technically a 1/2, right? This 2 on the bottom could be written as a 1/2, so that 1/2 in the dx can be replaced with the du. And then I have 1 over square root of 1 minus u squared, and now it matches up perfectly with our purple sheet. And we can write this as sine inverse of u plus c. Now there's the work. So in these advanced methods, what we're looking for is what does it match up with? How would I or could I factor manipulate to make it work? So here's our next one. Which one does it look like the closest? This one, it looks like tan inverse. Tan inverse has a 1 plus x squared on the bottom. And you're going to notice for inverses, you know how we have sine inverse, tan inverse, and secant inverse on the first page? But on the back page, you have the useless ones. Sorry, don't want to make them feel bad. Mostly useless ones. Of cos inverse, cotangent inverse, and cosecant inverse. The reason you'll almost never use the back page is because they are basically the 3 on the front page just with a negative in front. And you could just use the front page and just keep the negative rather than having to memorize the back page and have different ones. So you have that as an option. So what are we going to do? We need to take this 1 over 9 plus 4x squared and factor out the 9 because we want a 1 plus. The formula has a 1 plus, so we need a 1 plus. And then my 4 over 9x squared, my formula has a 1 plus something squared, so I need to rewrite the 4 over 9 as 2/3 x, all squared. The integrand is what's inside the integral. Just like a radicand is what's inside a radical. No, it's the word for what's inside an integral is called the integrand. I wonder if that, so same thing, radical, you take the AL off and add A and D. Radicand is what's inside a radical. Integrand is what's inside an integral. What other words end with AL in English? Sound a good word? What is it? Reciprocal? The reciprocand. I like it. What's inside the reciprocal? Nice. Might be a word. We could look it up in the math dictionary. So we'll do substitution, not because we have to, but just because it makes our life easier. So now we can replace the 2/3 x with u, and we have to replace the du with 3/2. Multiplying the 1/9 and the 3/2 gives you 1/6, and here we have our nice tan inverse of u, substituting back. Okay, question. How many of you, by the end of the unit, liked trig identities? Because what this advanced techniques is really like is like trig identities. You have something you want it to look like, and you have to do manipulations, factoring, substitutions, and stuff till it looks like that. So first of all, we recognized that this looked a lot like or similar to a 1 plus x squared on the bottom, but it wasn't perfect. So we manipulated, we factored, we rearranged until we got it to look like that after substitution, and then we could solve. Another technique that comes up often, I like to call unadding fractions technique. Because you guys are good at adding fractions. Here's an example of, I know you can add these fractions. What is x over 4 plus y over 4 equal to? They have a common denominator? How do you add fractions? You would say x plus y over 4, right? That's how you add fractions. You add the tops, keep your denominator the same. Unadding fractions is when you undo the adding. This is sometimes helpful when you kind of want to use substitution, right? Like if the inside function is 1 minus x squared, substitution would work out nice if the derivative of negative 2x or something x was present. But the problem is we have the something x, but we also have the 1. Doesn't quite work for substitution. We also noticed that if you had a square root of 1 minus x squared, which one does that match up with? Having 1 minus x squared on the bottom? That sure looks like it's a sine inverse. But it only works if there was just a 1 on top. So I'm going to, I don't think this is even a word, but I like it. We're going to make this up. I like making up words. The unadding fractions technique. The only word that I'm not sure it's an actual word is unadding. Unadding seems like you should write subtracting, but it's not subtracting. Unadding fractions technique says, let us rewrite 1 minus x over the square root of 1 minus x squared as two fractions separate. Because when you integrate things that are separated by adding and subtracting, you can integrate them separately. And if we unadd those fractions, the first one is beautiful. It matches up perfectly with sine inverse. And the second one matches up perfectly for substitution. Because now if I make my u 1 minus x squared, then my du would be 2x, and that would get rid of the x at the top, and things will work out. So our integral would be integrating them both separately. The first one is so easy, I'm going to cheat and show us the answer already. The first one is going to be sine inverse of x. And I'm going to uncheat and hide it. The second one, you are going to need to use substitution. If you let u equal your inside function, then your derivative would be negative 2x dx, but we just have a negative x dx, so I'll move my half over. Okay? And here I put a plus sign and kept the negative with the x. Perfectly fine if you kept the negative sign there and kept the x positive and did your substitution with positive values. It will make absolutely no difference whatsoever. But now, the first one we know is sine inverse of x. The second one, once we do the substitution, you're going to have u on the bottom in a square root, so I'm going to move that square root to the top and make it u to the negative a half. And then the negative x dx gets replaced with a half du. Sorry, there would be no plus c yet. And now we can integrate. Well, I guess technically there would have been a plus c with this one. I don't know. Notation-wise, I'm kind of bothered me. I'm a little bit bothered by notation right now. So we'll just, the best thing I can do with notation is pretend I didn't do this. Then I'm feeling okay, notation-wise. If you integrate something, indefinite integral, you need the plus c. But if I added a plus c in the first one, and then technically add another plus c in the second one, those plus c's might be different. And so I would need another letter, and I just think that's not necessary. So I'll just integrate all at the same time, so I just have to do plus c once. And then, of course, we could substitute back. The 1/2 and the 1/2 cancel out. U to the 1/2 is a square root of 1 minus x squared. And so by unadding fractions, we get things to match up. So I'm going to get you to try the next one on your own. Recognition-wise, you have something plus x squared on the bottom, which should make you think of tan inverse, which has the 1 plus x squared on the bottom. You have the 4 plus x squared on the bottom, which should make you think of substitution. If you make u equal to 4 plus x squared, then the derivative is just 2x. But the problem is on the top, you have 2x plus 1. So we are going to think about using the unadding fractions technique. Because we've got a bit of substitution that would work, and we've got a bit of inverse functions that would work. So we break it up and do both of them.